use this triangular segment, and I want to make 4 cuts of this segment on the 4 sides. So I use something called the replicate feature. It's very useful, easy to use. I right click on the component I want to make a copy of, and I say make me 3 copies of this thing, and boom, I've got 3 copies of this thing right away. Okay, so in terms of speed, it's very quick. It gets you there. The last thing I will make though is the beam. So that will complete our model building. The model building, if you're good at this, it should take you all of 5 minutes. Okay, this is again a very simple model, but 5-10 minutes you should be good to go. Okay, the last thing I need to add, like I said, is the beam. It's a component called the beam path. I'm going to quickly create a beam for you using existing parameters that you see on the side here. The beam is defined as beam. Oops. The beam path allows you to define multiple segments. So a beam can be made up of one segment coming this way, one segment going. It's basically like an L shape or serpentine beam, making different parts of it. And the beam path allows you to do that very easily. Okay, so it's like the end point of one beam is the start point of the second beam, something to that effect. One last segment is DC. So there's a beam. Okay, oops, I put my angle off a little bit. Well, I guess this is good enough. Let's say that we want to make 4 copies of this beam. Okay, so I select the beam component. You can see the beam component is right here. Okay, and it's not been defined correctly because it's from the center, but this will show you how things work. I can make a copy of this exactly the same way like I did for the cut. I select the component I want. I do replicate. I make 3 copies of that at 90-degree offsets, and there we go. Okay, so that creates our suspension of the device. So this is our completed model. Now there are electrodes at the bottom which we can add, and I'll maybe add one just to show you how it's done. Every rigid component comes with its own electrode. So typically for MEMS you have a plate on top, electrode at the bottom. I do right click, add electrode contact. The only thing I need to describe really for the electrode is what layer it sits on, because it inherits, you can see inherited on top over here. It inherits most of the properties from the parent, so things like shape and all that. I just have to say it sits on the electrode layer, and boom, that's my electrode there. Okay, so that's how you create geometry very quickly, right? So I'll show you what the completed thing looks like. I'm going to open the ready-made model. Do you want to save? No. Okay, so that's what it looks like. Obviously you can see the beams are now defined correctly. I think I may have missed something earlier, but this is what the full device looks like. Now this is almost ready to be sent to MATLAB. It's not there yet. There's one more bit that needs to be done. That one bit is the connections. Okay, now here you can see there's a bunch of black spots and a green spot. Okay, now this model that we have, okay, is, like I said, we use Legos to make it. We're taking one Lego block, sticking the other Lego block, bringing it close together, but we've not told it how they stick. Okay, we need to tell it that you need to plug into this part. Now a lot of this is done automatically. There's this thing called the auto connect, which is, I've used it, so it's grayed out at this point. This one, it automatically figures out that this beam is connected to this plate, that plate is connected to this beam, so it automatically fixes it. Okay, so the auto connect speeds things up greatly, and that's the last bit you have to do, is define which connection points exist, and the black connection points are mechanical anchors. These are fixed to ground. So I can pick that point and I can say ground. It's been grounded already, that's why it's grayed out. So when I hit the ground symbol, you are mechanically and electrically ground. Well, this is a mechanical ground. It holds that in place. So that is now your anchor. Okay. So mechanically, I'm set. This is all I need to make my device. One thing I didn't talk about earlier is the concept of exposing variables. Exposing variables, now I know it's not very clear in this projector, but some of these have a little E next to them. This is beam E, side E. E means exposed, means these variables are available downstream in Cadence or MATLAB as variables or parameters that can be changed. So I can go into Cadence and say, okay, beam change in Cadence or change in MATLAB. I do not need to come back into this tool. So this is the power of parameterization, is I define it here and it's available for me downstream to modify as I see fit. Okay. Any questions here? I was going to jump into MATLAB at this point. Okay. So this is the completed model. As always, hit the save button. It'll save your life. And it's saved as a .3D SEH file, okay, 3D schematic file. And this file is what MATLAB is what MATLAB will read in to make a model. Okay. So I've got MATLAB up here. The version of MATLAB that we use, it has to be a 32-bit as of today. We do not run on 64-bit, maybe in the future, but with MEMS plus 2, it runs only on MATLAB 32-bit. I've got 2009B, the version of MATLAB. Any version after that should work as well. I believe 2008A also works. I haven't tried that myself, but I think our documentation also says that. But 2009B, I know it works, and that's what I have on 32-bit. That's all you need to remember. Okay. So how you work MATLAB is, let's just open a new model. I'll show you how to bring it in, then we'll just use the schematic. I say new model, a blank Simulink window pops up. Now when installed correctly, you will see a new tab that says MEMS plus. Okay, that is when all the paths are defined correctly. So I can say MEMS plus, import MEMS plus model, and I can now choose which 3D SCR file I want. So I have multiple versions. I'm just going to use, let's say, the first one. So it thinks for a second and it brings back the model from MEMS plus, and you can see that there are a bunch of inputs that go in. I've not asked for any outputs here. I like to see my outputs in MEMS plus, so I don't ask it for it in Simulink. You could do that as well. But the pins that go in describe the initial conditions, okay, describe the stimulus, describe the voltages, any reference frame inputs there may be. Okay. So the TAY, the first 6 is the linear and angular accelerations. So this is like putting the device on a shaker table and shaking it all over the place to see how it mechanically responds. This is the mechanical stimulus that goes into driving this device. The bottom are the VDC, V bias, and VRF. These are the electrodes that belong to the device. There is the RF electrode, which is the central electrode. So in the device, once it's built completely, there's 3 electrodes because there's a top plate, that's one electrode. There is the bottom plate, the outside bottom plate, it's called DC, and the RF, which is called the center. So there's the center, concentric circle around it, and the plate on top, 3 electrodes. And 3 electrodes show up as 3 different points, 3 different inputs at this point. You do not need to put anything on it. You could have it as 0 bias, and that's what I'm going to use. I'm not going to put a bias on it now. Maybe in the next simulation I might, but for now I'm not going to use it. Once we have this model in, I start putting MATLAB components around it. So there is this library that I have in MATLAB. I'm sure you're all familiar with that. I can start looking for sources and different devices, grounds, things of that sort, start putting models on there. Okay. So I'm going to open an existing model. This takes another 5 minutes to create, so let's not waste time. So that is a built-up schematic. Okay. Now it looks fairly simple. We have shown you at least a slide of a more complicated device, around, a more complicated circuit around this, but this is a very simple device, so it's a fairly simple schematic. We've grounded the reference frames because we're going to put a stimulus on it in the next step. We also grounded the voltages, so there's no voltage on this thing at all. Okay, everything is at 0 bias. This is the model we're going to run. If you double-click the MEMS plus model, it opens up the parameter window. So if you remember, I exposed certain variables, the beam variables and the side variables. These variables are now available in MATLAB as something I can change. So at this point, I do not need to go back into MEMS Plus and say beam, you change. I can change that within here, and I can get a parametric simulation done through MATLAB. Okay, that's the power of having done things this way. If I do want to change a beam and it's not described here, I have to go back and do it. But now I'm all ready. Okay. So Steve mentioned earlier the three things I'm going to run are first an AC analysis, okay, a frequency response analysis. Second is a DC analysis, which is I'm going to sweep the voltage on this thing to try and find pull-in. At what point does it snap down and make contact with the bottom? And third thing I'm going to run is transient, where I'm going to put a voltage pulse on one of these pins. I think it's the VRF or the V plate, I don't know. I'm going to put a voltage pulse on it, basically disturb it with the voltage and release it so it goes, bounces around. Okay, 3 results. So for the AC analysis, as always in MEMS Plus, in MATLAB with MEMS Plus installed, you always run it through this MEMS Plus tab. There is the first thing I'm going to do, AC analysis. It pops up this window that describes the settings for the AC analysis. I need to describe the range. What range am I looking for? So I'm going to start looking at 0 and end at 50K. And I'm going to look at 1,000. Oh, that's a lot of points. Let's make it 1,000 points. I'm going to look at 1,000 points within this range. Obviously, the more number of points you have, the longer it takes. This should take about 30 seconds, I think. And let's make it 10,000. 30 seconds is not too bad. Second is the sources. Now, this is where I described to you earlier. This is like the shaker table. How do I want to disturb this device? This is a mechanical stimulus. So I'm going to say that the AX, AY, AZ, TX, TY, TZ is the linear and the angular accelerations that disturb this device, and they have these are the units. Now, this is a linear analysis. So the output is directly related to the input. So the more you force it, the more amplitude you get out of it. Okay, the shape will be the same, the mode will be the same, but the amplitude of the mode will be different. The 1e minus 6, this is in SI units, is a good number to start off with. That's a good scale number. This has been historically accurate for all of our other tools, and it seems to work here as well. So start off with 1e minus 6. If you think that if there's a g force, if you drop the thing, you may have a higher number on z, and you would change that here. You may, let's say, 10e minus 6 or something like that. Okay. But for now, just let's run with this. An output is blank because I'm not going to look at output here. I'm going to look at output in MEMS Plus. If you do look at output here, I would have 3 or 4 pins sticking out, let's say capacitance, displacement, whatever, and I'd have those listed here, and I could look at that from here. So when I hit run, it goes ahead and thinks for a while. It takes about 30 seconds to run, but what we should expect to see at the end of this is now, nothing interesting happens in MATLAB. MATLAB just finishes and just keeps quiet, doesn't tell you much. So I'm going to go back into MEMS Plus. I'm going to open this model in MEMS Plus and see, okay, what exactly did MATLAB tell me? MEMS Plus has a 4th tab. It's not a hidden tab, but it only shows up when you're looking at results. When you start up, you see materials, process, innovator. When you open up results, you have a 4th window called Scene 3D. Okay? Scene 3D is the result visualizer. This has existed for quite a few years now, almost 3 years, but this has been added to MEMS Plus as well. So I say simulation AC, that's the result that just finished. Obviously .AC extension stands for AC analysis. I open it up, and it brings in the completed simulation from MATLAB. Now, as you can see, MATLAB says analysis completed in 30 seconds. So this is one of the reasons why this is such a powerful tool. You can parameterize things, you can modify things, but you can also get good results in under 30 seconds for these kinds of analyses. Okay? So this is the device. You can see it's been colored. Right now it's not doing much, so it's all 0. I'm going to bring in results from MATLAB. So I have this 2D plotting window here. I'm going to say plot for me the center of this plate. How does it move? And there's your characteristic response curve. There's no damping in this device. I've not put that into this. I've got some damping in the transient analysis, so we'll see the thing oscillating and dying down. But this is a simple AC response of the device. It looks like it resonates at somewhere around 12 kilohertz, little under 12 maybe. But now I have an AC analysis here. Now in MATLAB, this is what you would see. It's like a body plot type output. This is okay, but I want a physical, image of what exactly is going on. That's why I look at the 3D results. So I can say move progress bar here, and then I can look at, okay, that's my first mode, and sure enough, that's what you would expect to see for a device that's fixed on all four sides. The thing is moving up and down. Okay, so in all of 30 seconds, we've got a good result from here. And once things are here, then we can start doing different things like scaling it up. And this looks a little bit better. It gives you a better idea of what's going on. You can see that it captures the bending of the beams. Now this is the detail that is not captured in this device, in this curve. Yes, it will show you that there's a Z displacement up and down, but for the higher level of detail, like the bending of the beams and things of that sort, you definitely want to look at 3D. Okay? Any questions? Okay, so that was an AC analysis. The second thing we're going to do, it's just as fast, is a DC analysis. A DC analysis is a DC operating point is a static result, it's a static analysis. We put 0 volts on it or 10 volts on it and see how the initial displaced condition is. Okay? What I'm going to do is I'm going to sweep this number. I'm going to sweep the voltage from 0 to 10 or 0 to 15 or whatever and see at every one of these voltage points what happens to this device. So I'm going to get a curve as the voltage goes up. I'm going to see that the device starting to pull down. So I go to DC analysis. I say I'm going to start from 0 volts. I'm going to go in steps of 0.1 to about 15. I think I've defined that right. So MATLAB again goes ahead and thinks, and it's done. I think it's done. So I can now stop this. And I look at the result called DC sweep. So now it loads up the result called DC sweep. Again, that took all of what? 2 seconds, 1 second. I can close the earlier tab, I don't need that. So again, this is the starting point, everything is colored blue, this is 0. I can look at now the curve. And as usual, I'm going to look at the plate center. And there's a nice pull-in curve. Okay? This shows that as the voltage goes up, it starts coming. You know what? Let me just run a movie for you. It speaks for itself. And let me scale this up a bit. Oops. Okay, there we go. So I'm going to run this, and you can see as the voltage goes up, pulls down, and snaps. Okay, so that's a nice pull-in analysis. What you should notice here is that we're simulating contact. Okay, we're simulating pull-in, which is an instability. We're running full electrostatics on this thing. Well, at this point, yeah, DC. So we have electrostatics on this thing. So all of these combined multi-physics, we've got, and we know this is right because in the afternoon or after this, I'm going to run this in FeA and show you how well they match. The pull-in voltage is about 13 volts on this, I think. Well, this is step number, so this needs to be multiplied by 0.1. Anyway, so this is about 13 volts. Just remember that much. Okay. So this is a DC analysis. Any questions? Okay. I assume that means everyone understands. Okay. And finally is transient. Transient response is when you disturb this device either mechanically or electrically, any way you want, and then release it and basically look at the time response of the device. Okay. Now for that I have a different schematic. You could put them all in the same model, but just to make things a little clearer of everybody. So this schematic looks slightly different. Most of it is same. The only thing I've added is a little pulse generator. I'm going to create a voltage pulse to hit this thing a little bit and let it go. Okay. I won't talk about the initial settings and all that. It's all there in the documentation, so please read. I hit the play button, and again, it takes all of 2 seconds maybe. I don't know. and a transient result is done. So here you can see the input. Okay, this is what goes in. This is the pulse that disturbs this device. As usual, I'm not going to look at this in MEMS in MATLAB. I prefer the plotting in MEMS Plus. So I close this. I close the DC sweep. I go to this, and I say details, and the result is .trans for transient. I open it. And I do the same thing as before. I plot the center of the plate. Now you don't need to do it this way. I could just run this, okay, but it doesn't really show you what's going on unless you have the curve with it. So what is happening here? So we have, if you notice, we have two pulses. We have the first pulse, okay, that's about here, and the second one over here. So we're shocking this device. It starts oscillating, and we have some damping in here, so it starts settling down because of the damping in it. And once it starts getting to about 0.005, the second pulse kicks in, and that again pushes it all the way to the top. Okay, and the second cycle starts. So this is a transient result of the device. I'm going to now scale the thing up so it's a little bit easier on the eyes. Loop it up again. Let's make it a little fatter. There we go. So if you slow it down, a slightly more dramatic response. Okay, it slows down there, and now it starts getting disturbed, and bang, goes back up, starts settling down. Okay? So this is it, a transient result. Again, took all of a few seconds. So this is the power of a tool like this. You have complete parametric variation. I've not shown you that yet. I don't know if I have enough time. Do you have enough time for one more thing?
I think we probably want to move on to Coventorware.
Okay, all right. But we have parametric variations as well in this. That's described in the documentation. So please look at that. But this is it. This is MEMS Plus with MATLAB. This works the exact same way with Cadence as well. So if you're going to use Cadence, same rules work, same things work. I personally prefer MATLAB. I find it easier to use, so that's my way of doing things. Okay, any questions? Yes?
So without MATLAB or Cadence,
Mm-hmm.
the architect has the same function as this?
Yes, Architect has similar functions. I would call MEMS Plus the superset. So Architect, yes, can do a lot of what this does. You've used Architect in the past?
No.
Okay. Okay, I assure you, once you see this, you will not use the other one, simply because it's a lot harder to use. Okay, this 3D interface doesn't exist in Architect. Okay, this one doesn't exist. The way you create a model in Architect is by using something, you have the same library of components, but it looks like a circuit representation. So it's not very easy on the eyes, and it's hard to understand what you're seeing. It still does work. It does a very good job of doing the same kinds of things in the same order of speed, same kinds of results, but it's harder to use. So I've been spoiled by this. So if you want to start with Architect, go on, no problem. It'll work. Any other questions? Okay, thank you for listening.
Out of curiosity, how many people are interested in trying MEMS Plus based on what they've seen?
Yeah.
All right.
Okay.
Great.
Job successful. So, all right. So Steve's going to talk about Coventorware now, which is our other set of tools, FeA Tools. We've mostly seen that. And once he's done with that, I'll do a quick demo on that as well for those of you who haven't done it. And we'll do the same device on that as well. Okay? Thank you.
Important. What the pizza's arriving when? At 12:15, or that's the target?
Yeah.
Okay.
So it's all yours. Hold on. Okay.
Yes.
Do we have any plan to install NEMS Plus? Yeah.
I don't know. That's up to. We certainly wanted you to be aware of it, and quite a few other universities have adopted it now. So. All right, back to Coventorware, our flagship product. As I said before, Coventorware is, there are three main parts of Coventorware: architect, designer, and analyzer. I'm going to focus and MEMS Plus with MATLAB Simulink, the 2.0 release that's coming out this month, is really, we hope, will be a replacement for Architect for most users, and it's really a friendlier place to do your modeling. But Architect is still available, and I guess is available at the center here. So, and it's a perfectly good tool. But I wanted to focus on Designer Analyzer. So Designer, we start, again, I'll just review this. We did it earlier, starting with the materials and process data as we do in Architect. From the layout and the process, you build a 3D model, and you have access to it in the preprocessor, and then access to automatic meshing. So we'll take a little bit closer look. The layout editor, one of the key things about our layout editor that's important to know is that you can enter true curves. So if you have fillets in your design, they should be represented as arcs or vias, circular vias, or curved areas, they're splines. That is one of the key things, and the reason why is that when we subsequently use that layout to build a solid model, we get nice smooth surfaces on the solid model. If, on the other hand, you have a circle that was drawn in a GDS2 layout, that circle is actually a polygon with lots of sides. And when you import that polygon to our layout editor, it stays as a polygon. We have tools to convert it to curves in our layout editor. But if you go straight from GDS2 into a solid model and there are curves there, you're going to get a solid model with lots of facets on it. And that in turn is going to constrain the meshing, perhaps cause a lot more mesh resolution in places where you don't need it. So that's a key point. Another thing that's worth learning how to use is the hierarchy. So most MEMS have some repeated structures, and it's worth learning how to create a cell that's then going to be instantiated at multiple places on the layout, because then if you want to change your design, you just change it in that one cell, and every place that there's an instance of it, it changes. So that's worth learning. And we have export to standard layout formats. There are a set of parametric MEMS layout generators largely tied to Architect that may be useful to some people, but I would say those other features are the key ones. Another area of it is that there's a layer browser where you set up the mapping between layers and masks. Because your mask may be composed of multiple layers, that mapping between layers and masks is shown in the layer browser. There's some built-in design rule checks that we've developed over time that you can run interactively or in batch mode. And there's from the layer browser, there's something called a mask viewer, where you can actually see what the dark field and light field is going to be in each mask, and that's a helpful tool. The process editor, it's designed to, again, we're not doing, in Designer, you're kind of doing a process emulation. It's definitely not process modeling like we do, or virtual fabrication, because of you're looking to just capture the features that are going to be important for finite element analysis. Nevertheless, you can name steps to correspond to steps in the fabrication process. There's this hierarchy can be customized, so you can have sub-steps and sub-steps of sub-steps. If that's a helpful way to document what you do, you can activate and deactivate steps, so there's reorder them and so forth. On the right side, there's a library of pre-configured steps, and you can customize this library. If you don't see something in here that you want, the file that contains this library is actually just another process file, and through the Tools menu, you're able to edit that library and add your own steps to it. Also in there, there's a library of foundry processes, and we have quite a list of foundry processes that come with Coventorware. So if you're just starting a design or learning, this is a good thing to do, is use one of these foundry design kits. For each one, the data is available as a material property database that we've worked with the foundry to validate, and a process file. Some foundries have more than one process and variations on a process, so you'll find them. These are documented in our documentation. There's also a layout template that has all the layers that are needed for that foundry process, and some case studies and tutorials. So here's the list of foundry processes that ship with Coventorware. And if you're trying to, again, if you're getting started, this is a good place to start, or learn about MEMS to look at other people's processes. The solid modeler is mostly hidden to you. It's taking that 2D layout and the process description and building up the 3D model. And it's emulating real foundry steps, deposits and etches, but not in a way that's ideal for subsequent modeling with finite elements, but it's not as realistic as what you get out of Simulator 3D. And then going into the preprocessor, once you've built, the solid modeler automatically opens a new model in the preprocessor, and you have lots of visualization capabilities in there, cross-section planes, plus under the solid model menu, ability to partition the model with planes, transform, do geometric transformations, translate parts, rotate parts. You can, as you choose which layers you're going to do an analysis on and drag them into the mesh model folder, it automatically figures out which layers are touching and merges them, which assures that you get a conformal mesh on those layers, and that's important for finite element modeling. And it has access to our mesh generators and mesh quality checks. The meshing in Coventorware is really ideal for MEMS type geometries, and we have a 5, at the top level it's 5 that's actually under the covers. There's probably about 8 different meshing algorithms available that find uses for different kinds of geometries. So there's a Manhattan mesher that generates bricks that works not just for pure Manhattan, but for slightly non-orthogonal geometry. And where that can be useful is oftentimes with MEMS like DRAE, you'll have slight sidewalls on the process. And you can it'll still work with those sidewalls there, if certain sides are not perfectly Manhattan. Manhattan means 90 degrees angles between everything. That'll work. There's a brick mesher that does extrusion for cases where Manhattan doesn't work, and it'll extrude through multiple layers. We have, for sometimes, the best way to get a mesh is with map meshing, and you have to decompose the geometry into 6-sided parts. So, for example, this pressure sensor membrane was done with map meshing to generate nice uniform mesh over the parts with these sloped sidewalls. Tet meshing is probably the last choice for volume meshing, because it's oftentimes, especially for MEMS type geometry, it's hard to get good quality tet meshes unless you make them really fine, but it's there, and for certain geometries that might be the only way to do it. And then finally, because we have these boundary element solvers, there are surface meshers, and typically stationary electrodes just need to be surface meshed, so those can be done with triangles, quadrilaterals, or a mixture of the two. You have lots of local refinement controls, and basically on every level of the model, which is available in this tree, or selecting on the canvas, you can set a mesh size or other mesh parameters that are going to override higher level values. So for example, you set a mesh size of 8 on a whole layer, and then one part in the layer. A layer can have multiple parts, needs to have a smaller mesh. You select that part and bring up the mesher settings and set the mesher setting as 6 on that part, and that part will get a nominal size of 6. Everything is 8. And you can do that right down to faces, edges, or vertices. So it's really quite powerful. A lot of people aren't aware that that feature is there, but it is available and very useful. And then there are quality checks that help show you what the overall quality of the mesh is, as well as highlight bad elements in the mesh. And finally, we know ANSYS is out there and a popular tool for MEMS, and we have the ability to import and export ANSYS meshes. The one sort of potential gotcha there is that we don't import the material or export material properties. So if you're going to, you can get the mesh in, but you're going to have to manually transfer the material properties from one tool to the other. Also with Designer, there's a library, a standard package library with over 30 packages from Kyocera and Hymite. Each one is, the solid model is pre-built and it's pre-meshed. So for things like looking at choosing a package, this can be helpful, or looking at the effects of the package deformation on the anchors of your MEMS device. This is a quick way to get started. I showed this before, but again, Coventorware has lots of ways to get in and out of Coventorware. And then in Analyzer, there's a set of field solvers, and you choose from MEMS or microfluidics, and then choose from this suite of field solvers. We have a lot of support for simulation management. There's a full relational database that runs under the covers of Coventorware that tracks relationships between meshes and results. So, and you have a browser that lets you browse that database and find old simulations easily. And you can have some ability to annotate them in there. And we also, one of the things we added with Coventorware 2008, and of course ongoing, is a job queue that lets you set up multiple jobs, submit them, and they sit in the queue. You can put a job on hold and let another job run before it. You can abort jobs and so forth. So that's a very convenient feature for simulation management. I should also add in this area that all of these solvers support parametric studies. So not as powerful as what you can do in MEMS Plus, but you can do define 1, 2, or 3 variables that you're going to vary, and it automatically, there's a parametric study option when you start any simulation, and you can vary those variables to get a set of results. And finally, the post-processing provides, for each solver, it provides appropriate list of tabulated results that you're likely to want from that solver, and that might be the first place you look. And then in addition, you have the ability to look at everything in a visualizer, and that visualizer has more options than you can shake a stick at. I mean, it can do almost anything you want, but that means it's also somewhat complicated to use, and you have to, it takes a little patience to get used to it sometimes. Reviewing, the real strong suit in Coventorware is electromechanics. Pure electrostatics, we have MEM-Electro, which is a boundary element solver, MEM-Mech, which is based on Abacus for mechanics and piezoelectrics, and all these other things listed. And then recently we added to MEM-Mech electrostatic elements. And actually, this was partly a response to to be perfectly honest, to our competition from ANSYS, because they have electrostatic elements. A lot of people use them. The thing you got to watch out for is, and people generally, I think, aren't aware that the elements in ANSYS and ours don't have fringing fields. For devices like comb drives, those are not likely to be very efficient. On the other hand, for devices like this Varactor, where Sham showed you, the fringing fields probably aren't that important, and you can use this approach. And in fact, Sham is going to show you Actually, you're going to do CoSolve, right, later? Okay, but we could do it with this MEMMAC. Why would you do this? Well, these simulations run a lot faster than they do in CoSolve, so trade-offs. Accuracy versus speed is usually the trade-off. And the other thing we added recently is a variant of CoSolve EM called Harmonic EM to do modal coupled harmonic analysis. Another thing that's unique to MEMS is that you need to worry about gas damping, and we have a module called MEM damping, or is it MEM damping or damping MN? Damping, it actually should be damping MM here, that does damping in two different ways, 3 types of damping, but with a Reynolds solver and a Stokes solver, a separate solver for piezo resistance, and then a solver called MEM Henry that does frequency-dependent resistance and inductance. So I'll go through this quickly. Again, the CoSolve EM, which is certainly the most heavily used part of Coventorware, uses the MEM electro for electrostatics, MEM mech for mechanics, and iterates between those. And you can do things like pull in and lift off with that solver, and that's heavily used. The new electromechanics in MEM mech, you essentially have to define, you don't have to actually mesh the volume, you have to use a volume mesh on both the moving part and the static electrode, and define a boundary condition such that those two know that they're talking to each other, and then in the solver it automatically generates these electrostatic elements. And you can have whatever shapes you want on either the moving or fixed electrode, and it performs static analysis, harmonic analysis, and transient analysis. Here's an example of transient analysis of pulling in a beam. So note, in comparison to CoSolve EM, which does quasi-static analysis, this is full transient, but again, the fringing fields are neglected in here. We added one more thing to MEMMEC in the Coventorware 2010 release, which is the ability to include squeeze film damping, and that can be applied in transient analysis. What's interesting, it's a fully nonlinear version of the Reynolds equation, so that as two things come into contact, there's a lot of nonlinearity that happens there, and this implementation captures that. Sort of a caution is that this solver, we're still improving it, and occasionally when your things come into contact, you might have difficulty getting it to converge, and that would be an opportunity to call your friendly Coventor support team for help. So here's an example of a transient response to increasing a voltage on a cantilever, and with no fluid damping, it pulls straight in and until you get contact, and then with fluid damping, as it gets closer to the bottom electrode, you can see that the motion slows down and it's starting to be buffered by the gas in there. So this is a powerful, unique, new capability. I also mentioned Harmonic EM is new. It's a coupled solver that uses MEM electro and MEM mech. What it does is it first finds the equilibrium state under DC bias, so that's CoSolve inside, performs a harmonic analysis about that equilibrium state, from which you get a spring softening effect, and it outputs the harmonic displacement and current versus frequency. So that response includes stress stiffening effects, which and electrostatic softening of the resonant frequency due to the DC bias. Here's a very simple example, a plate on 4 tethers with 3 electrodes underneath. What we do is we put a drive voltage on the 2 outer electrodes. We want to get output from the inner one, and the output's going to be a current, and we have to have a DC bias between the plate and the electrodes in order to get any output. And so a straight modal analysis of this structure gives you this frequency, 22 kilohertz and change. stress stiffening. It predicts all of this stress stiffening. It goes up a little bit because these tethers don't have any, they're fixed at the end. And then due to electrostatic spring softening, due to this bias, you can see the resonant frequency goes down almost more than a kilohertz. And here's the output. You're able to get the displacement versus frequency and output this current on the output electrode versus frequency. So with these outputs, we don't have an example here, but one can model this resonator as a two-port network, and you can use a two-port network theory to come up with the impedance matrix for this two-port network using this solver. And so this is a new capability, and that once you have that two-port network impedance matrix, then it's some more algebra to get from there to S parameters that you'd want for a resonator. Here's a little more complicated example, a LeMay mode resonator, which we apply voltage on one pair of electrodes. We expect output current on the other. This is going to oscillate. Maybe it'll oscillate. I guess not. All right, so it's a breathing mode. These sides go in and out. This one, it's kind of a breathing type structure. And you can see as you change the bias voltage on the resonator, spring softening causes the natural frequency to reduce. So at higher bias voltage, 200 volts, you've got a lower natural frequency for the resonator. And for 0 volts bias, you get almost no output. And so to get output from a resonator, an electrostatically driven resonator, you need to have bias voltage. So to summarize the electromechanics, there's quite a bit of choices in Coventorware from Architect or MEMS, and really this should say MEMS Plus here, which can, and various effects that you may want to include or types of analysis which are listed across the top. So do you want fringing fields or not? Are they important for your device? Can you do quasi-static analysis? Can you do pull-in lift-off analysis? Can you do transient and so forth? And you can see that Architect Architect or MEMS Plus do all of them. The only thing it doesn't do is harmonic analysis using a modal approach. It's using a direct approach, but you can still get at the mode shapes. There's one other thing about the MEMS Plus approach. Because it's based on these analytical or semi-analytical models, you can't really do a convergence study. And that's really important because with finite element method or boundary element methods, discrete methods, you always have the ability to make the mesh finer, and if you keep making it finer, eventually you're going to converge on the ideal answer. With Architect, you don't have that. You can do, there is some amount of tuning of the models you can do, but it means that and we've done a lot of verification of these tools, but ultimately, when you use these tools, you have to go and do some finite element analysis to verify what you've done. The tool still has value because of its capability and because it runs so fast. When you look at the finite element tools like MEMMEC with electrostatic elements, that has less capability. On the other hand, you do have this ability to do a convergence study so that if you keep refining the mesh, you can be sure you're getting a correct answer. And the same with CoSolve and Harmonic EM. So different capabilities, and this is partly why I encouraged this support sessions this afternoon. Coming into this, it's hard to know, what do I use? Well, this chart provides you some guideline. We have a lot of documentation, but it takes some expertise to understand. And in the same way, for piezoelectric analysis, we have lots of capabilities in MEMMEC, in MEMS, and in Architect, MEMS Plus, and it depends what kind of device you're looking at, which one is the best choice. One of the things that we added recently to MEMMAC is the ability to do modal harmonic PZE. Previously, we could only do direct harmonic, which was slow. It's a modal harmonic means there's a set of vibration modes that you want to capture in your model. And those modes together characterize the response. It's almost always faster to use modal harmonic than direct harmonic, and that's why we did it. It's of interest largely for very high frequency resonators based on piezoelectric effects. I'm just going to show some examples. So here's a comparison. You can get the same answers with modal and direct harmonic, but with modal you can really pinpoint those peaks, and again for resonators this is very useful, especially in with resonators where there can be a lot of spurious modes that are closely spaced with the modes of interest. So I won't belabor this too much. Another thing we added to MEMMAC is the ability to include circuit elements, and that's largely for energy harvesting applications. So in order to optimize a piezoelectric energy harvester, you need to be able to put a load on it, and so we added the ability to add simple circuit components, resistors, inductors, and capacitors to the electrodes of the PZE device, and that lets you then optimize the design of your energy harvesting device. So that so here's an example. I think I wanted to. Yeah, so you can see here this is with different resistance loads on a vibrating energy harvester. You can see that the peak power output, and of course with a harvester you're trying to optimize that power output, the frequency that power output occurs varies with the electrical load, and that's something that you can now predict with some accuracy, and we did quite extensive validation of our simulations with papers in the literature. There was in particular as well as an analytical theory by this fellow Erturk, who's at University of Virginia. As I said earlier, if you're talking about resonating, whether almost any kind of MEMS, but resonating devices like gyros or resonators, filters, you have to think about energy loss mechanisms, and you're particularly interested in the quality factor. And so the total quality factor of a device is a sum of the inverse quality. Total quality is a sum of the inverses of the component parts. Some of the things that are of importance in MEMS, gas damping, of course, and we have damping to address gas damping. You have thermoelastic damping, and we added options in the last few years to include thermoelastic damping in MEMMAC, so that's an option. And anchor losses, so somewhere this vibrating MEMS has to be attached to the substrate, and that's an opportunity for energy to be lost. And we have something called a quiet boundary surface BC in MEMMAC that lets you approximate anchor loss. And then there's other stuff, and usually that, the other means nobody's quite sure what it is, but they measure a damping coefficient and can't fully explain it. And the classic way to account for that is with so-called Rayleigh damping coefficients. And Coventorware always has allowed you to enter these Rayleigh damping coefficients. And MEMS Plus also allows you to enter Rayleigh damping coefficients. I'm thinking we'll get to the demo after lunch at this point. MEM damping really includes two solvers, a Reynolds solver and a Stokes solver. The Reynolds solver, I'll go into a little more detail, but if you take a very simple problem, two plates, the length is 50 microns, and we vary the gap of the plates, we see that for small gaps, these solvers the Reynolds and the Stokes solver, as well as a full Navier-Stokes solution, they agree pretty well. It's when the gap, the ratio of the gap to the length gets larger, so for larger gaps that these different solutions have different values, and we'll see that the Stokes solver, which is a 3D solver, compares well with the full Navier-Stokes equation for those large gaps, whereas there's some error in the squeeze film solver with certainly considerable error if you don't correct for what happens at the edges, and still some error if you use the edge corrections that are available. So again, you need to use some judgment. There's one off the point that's off here. That was just a case of the mesh being too coarse. The Reynolds solver definitely is, if you're in the domain where that is valid, that's the way to go because it's really fast. You can account for edge effects on holes, and it's really quite accurate. And you can even omit part of the things. And so with the Reynolds solver, you're getting two things. You're getting the damping force and the spring force versus frequency. And you can see that at low frequency, the damping force, which is, of course, in phase with velocity, dominates. And then at higher frequencies, the spring force, which is in phase with the displacement, dominates. And so you get this frequency-dependent behavior out of the Reynolds solver. The Stokes solver is, on the other hand, is more quasi-static. It's more compute-intensive. It can account for rarefaction effects or so-called slip boundary condition. And there's some other details about the computations that I'll just show you for something like a mirror pixel in the digital light projector that's rotating through quite an angle. With the Stokes solver, the damping coefficient for this mirror changes as it goes through that angle. So here versus angle, you see the variation in the damping coefficient, but you also see the effect of different rarefaction factors. So this is 0.2 atmospheric pressure. I think that's atmospheric pressure here with slip and with no slip. So accounting for slip turns out to be important and something you can do in the Stokes solver. So some guidance for how you choose a damping solver. Start with Reynolds. It's very fast, very easy to mesh, includes compressibility, and it's accurate if the assumptions apply. And the assumptions are small displacement, small gap. The gap has to be parallel, more or less, and it's useful for rigid body motion or mode shapes. And low Reynolds number, so you need to look at that. With all fluidics, you have to look at the Reynolds number. If those assumptions are violated, then you have to go to the damping Stokes solver, and that will take some more time, but available for arbitrary shapes and rigid body motion, best for non-interior flows. So if you have something where it's totally enclosed, it's not a good choice. And then if neither of these two is appropriate, then MEMS CFD, which is a full Navier-Stokes solver, is always an option. Next one is thermoelastic damping. I'm going to kind of, so this is just explaining what it is. It's the energy loss due to heat conduction across, so in this case, if this thing is vibrating back and forth, you actually have heat flow across the width of this, and that heat flow, there's a loss of energy, and that's actually a source of damping in some MEMS, and you have the ability with MEMMEC to compute that thermoelastic damping. And the other one is anchor loss, and you have to think about your MEMS device. You have to model a part of the domain that's at least equal to one wavelength. So you're talking about modeling quite a ways out from the MEMS device, but you're then able to get at the energy loss through the anchors. I went through some examples of Analyzer earlier. I would be remiss in talking about Analyzer if I didn't or Coventorware if I didn't plug our documentation. The documentation's evolved and improved. It keeps improving. There's a master help that's really a nice way to, it shows you at the top level guide through the flow. You can click on any one of these boxes and to get to dive down into the information. This is quite useful. There's 2 volumes of MEMS tutorials. So I know somebody earlier asked, could we have your slides? I'd say go to the documentation that will install when you do Coventorware. It's really, we get compliments on it frequently, and it's really comprehensive. As well, we have reference documentation, both the details of how you use any solver and the theory behind each solver. So just to, in case there are any existing Coventorware users, what we added in Coventorware 2010 were some of these things I talked about: Harmonic EM, modal harmonic analysis, circuit elements for harmonic PZE harmonics, and this gas damping and MEMMEC. And the solvers, the MEMMEC solver in particular, uses memory more efficiently. We keep improving the speed and capacity of the solvers. So right now, MEMMEC will run in 64-bit on a 64-bit operating system. The next release of Coventorware, Coventorware 2010, will be 64-bit throughout the flow. It runs on Windows 32-bit and 64-bit, so Windows XP 64 as well as Windows XP 32. And now it runs on Windows 7. And on Red Hat Linux, we've discontinued support for 32-bit Red Hat Linux, although it probably runs on it. But almost nobody uses it anymore. Most Red Hat Linux installations are 64-bit. So that's Coventorware. Designer Analyzer have a huge amount to offer. Again, there's years of development in these tools, and if it's MEMS, you can probably do it in this product. So what Sham is going to do next, and I don't know if we want to, is the pizza ready or? Okay, so we'll break for pizza, and then when we come back, Sham's going to do a quick demo of Coventorware.